All right, so before we start any calculations, let me go over what a buffer is and what acids and bases are. A buffer is defined as a solution that resists pH change. In a buffer, you must have an acidic component and a basic component. So what's acid and base? So when we were in Chem 1, we learned that acid is defined as something that when you dissolve in water gives off hydrogen ion. Base is something when you dissolve in water gives off hydroxide ion. So in Chem 2, we learn a new definition. It's called Bronsted-Lowry definition of acid. Acid is a proton donor, means it releases the proton. What in the world is a proton? Proton is basically H plus or H3O plus, which is called hydronium ion. Okay, H3O plus is basically H plus plus water to get hydronium. So basically it's just whatever form the H plus. So if it donates a proton, it's the same as giving off H plus, okay? Base, on the other hand, is defined as a proton acceptor. So when we come to Bronsted-Lowry definition, we have proton acceptor and proton donors. So basically if I have acetic acid, this is a weak acid because it's reversible. I'm showing you a weak acid and weak base example. Anything that's reversible like this means it's a weak sample. Weak acid or base, okay? So acetic acid, here's the formula, that's our weak acid, and then we add it in water, okay? So if this is an acid, water will behave as the base because water is always gonna just pair with whatever it is. It can change roles. You see water can have an acid also here. So a weak acid is going to release the proton, and when you lose the proton over here, all you get here is the acetate ion that's left over. This acetate ion and that guy here is a pair. This is called a conjugate pair, where a weak acid, after you lose the proton, you have a conjugate base left behind, okay? Now, this water here acts as a base because it was paired with a weak acid. Base is a proton acceptor, so all you do is that proton that they came off goes onto this guy, and you get H3O plus, which is now defined as the conjugate acid. So these two here are again a conjugate pair. Okay, let's take a look at ammonia. Ammonia is weak base because it's reversible here. Weak base is defined as a proton acceptor. When you put it in water, water will act as an acid because it just goes with whatever it's paired with. Weak base will accept a proton. Where in the world did that proton come from? From the water. Water will lose a proton because water is a proton donor. That proton goes onto this guy. So because this was a base that accepts a proton, this guy is called the conjugate acid. Again, ammonia and ammonium here are a conjugate pair. Now, water, once it's an acid, it loses the proton. One OH goes over to this guy. What's left over is hydroxide. Hydroxide here is called the conjugate base, and this is another conjugate pair. So notice water can be acid or basic depending on what it's mixed with. So we call this guy amphoteric. This is a special quality. Okay, there are a few other different amphoteric compounds, but right now we just need to know about water. So what's the difference between a weak acid, which is reversible, compared to a strong acid or strong base? So strong acid, strong base are not reversible. Okay, so if it's not reversible, they don't go like, oh, well, I want to be this, and then I want to go back there. I want to be this, and then go back there. They don't go back. It just, once it splits, it doesn't go back. The reason why we call this one conjugate base is because this guy has some basic property. Anything that came from something weak has the opposite property. So weak acid has an ion that's conjugate base because this is weakly basic. And it can, because it's a base, it can actually have the tendency to put a proton back on here to move itself back to this form, okay? Same idea for this guy. This is slightly acidic because acids can actually try to shed that proton off to make it go back to ammonia. It's possible. Strong acids and strong bases cannot do this. So whatever is left over, so like if you have hydrochloric acid, you have Cl negative here. Cl negative has no option but to stay there. It cannot say, well, hydrogen, why don't we bond back together so we can be in acid again? It doesn't do that. So Cl has no capability of attaching a proton, accepting a proton, so therefore it's neutral, okay? Sodium is the same thing. When you have sodium hydroxide, all group 1 and group 2, generally group 1 and group 2 hydroxides, group 1 group 2 metal paired with hydroxide is going to be a strong base. It's not reversible. So whatever's left over after you split with the hydroxide, like for example, sodium here, it doesn't have the opportunity to go back to bond with hydroxide to make itself a base again. So this is completely neutral. So Na and Cl here are options, are spectator ions because they're completely neutral. And it's become very useful for you to use these ions, spectator ions, whenever you need some conjugates. Like for example, if you needed a conjugate base supply, they don't sell acetate ion by itself. It comes as sodium acetate. So you would have to pair it with something spectator ion. Like you wouldn't be able to buy ammonium by itself, but you could find ammonium chloride because we would use this guy, which is a spectator ion that's completely neutral. Okay, so that becomes useful for us when we want to make buffers. So since we need to know what makes a buffer, let's talk about a direct way to make a buffer. Okay, so the first way is directly to make a buffer. This is what we do in part C, where you actually, depending on what pH you want, most of the time we talk about acid and conjugate base. Optional is if you want a pH buffer that's really high pH, you probably want to start with the base. That way you can get a different pH number. But you know, this one will be like buffers that can be made around maybe pH 4, pH 5. These guys will make buffers like around pH 10. So it just depends on what you need. So over here, you need to compare, to make a buffer, you have to add the weak acid and its conjugate base, the pair that it's with. Or you can use a weak base and pair it with the conjugate acid. So just for simplification purposes, I wrote down generic formula, like whatever the acid is HA. If it's a weak acid, and you want to make a buffer from this weak acid, you must mix it with some A minus. But you can't find A minus on its own, so generally we use NaA, whatever the ion is here, okay? Why sodium? Because it's neutral. Or you can use a base. If you have a base here and you want to pair it with a conjugate acid, you can't really have the conjugate acid alone as an ion. You actually will pair it with something with chlorine, with chloride. So you can see that because this guy is neutral, it won't really hurt anything. It's just a source for you to supply the conjugate acid. So how does a buffer work? Basically, it goes by self-sacrificing. So if you have a strong acid, what happens is the buffer component, the acidic component, well, if you have incoming strong acid, there's an acidic component of the buffer and a basic component of the buffer, right? So which one would self-sacrifice? If you have incoming acid, they will sacrifice the base component. If you have an incoming base, they will sacrifice the acidic component, basically whatever is the opposite to help it balance it out. So let's say hydrochloric acid was poured in. The real worry here is H+, because this H+ will change the pH dramatically. But because it's a buffer, the buffer has some conjugate base hanging out there. It will self-sacrifice this guy and react with the incoming H+ and turn it into the weak acid, which is another part of your buffer component. So basically it neutralizes this guy to make it another component of your buffer. So that's how the pH resists change. All the change is slightly less of this is available now, and slightly more of this is now available. Okay, you do have to be careful. The more H+ you put in, at some point you might put in so much H+ that you run out of A-, the conjugate base, then your buffer will break. But if you have enough A- in here, you should be able to defend against the H+, and the pH will not change dramatically. If you have an incoming strong base, what you'll do is hydroxide comes in, because if you use sodium hydroxide, sodium doesn't really matter, it's a spectator ion. Hydroxide is a strong base, then the buffer will have to self-sacrifice the acidic component of the buffer. So acidic component would be HA, the weak acid. Remember, because we're talking about the weak acid and the conjugate base here. So if you have weak acid conjugate base, so this guy here is like, okay, well, I'm going to self-sacrifice. Some of it will get killed off because they neutralize this guy. Okay? What happens when hydroxide meets weak acid? What happens is they like to meet and take the H and make water. What's left over is, oh, this is the conjugate base. So another component of your buffer. Really harmless, and that's why the pH doesn't change a lot. Okay, so basically, let's take a look here at some data that we have. So I printed out some of these data sheets here. You can find this on an Excel file. in student dry lab data file, and this is under one of the tabs here. So let me show you where it would look like if you were trying to look for it on Excel. So right here. We're going to look at the Excel file first. So if you look on the tabs here, this is my Excel file. All you do is remember the first lab, we have this, second lab, we have this, third lab. So this is our pH and buffer lab. And then you just scroll down, you have the pictures, all the information that you need. So this will all go into your recorded data section, okay? Of course, the following reactions here. One thing I want to let you guys know is 10 test tube, there's going to be a chart put on the results. There's going to be a practice quiz. So I don't actually put the results here, okay? On the quiz itself, the practice quiz will have the results, and you can use the practice quiz till you do well, and then you take the real results quiz. So here's the next experiment. Basically, all the experiments you need, all the data is provided, okay? So let's go back to pH and buffer. Now, let's head back and look at the questions also. So basically, we're going to walk you through how to look at these answers here by taking a look at our book here. So what I'm going to do is show you basically part A has these data, and that goes over here. Okay, so you basically it's all matching. And then this is part B's colors. And the brown crystal green tells you whatever color this is. Conjugate is this color. So I'm going to walk you guys through this color a little bit, okay? How can you use this color to get your answer? So let's say, let's take a look at the results section. So the first question in part A says, net ion equation for something that's basic. So you have to take a look, which one's basic here? So basic one will actually pick this guy, because in the instructions and the procedure actually tells you anything higher than, I believe, 9, okay? So that would be my basic one. And you remember, so they're saying sodium carbonate is basic. Why is it basic? Well, I just told you that sodium was neutral. So that means carbonate ion is basic. Okay, carbonate ion is basic. So if this is the base, what's going to happen is it's going to mix with water. The water would be the acidic portion. And then the base, the weak base here, is going to accept a proton to get HCO3 negative. And this is my conjugate acid. And then what's left over, because this is acid, it sheds the proton goes on here. What's left over here is hydroxide. Okay, so basically sodium carbonate is a basic solution because it gives out hydroxide in your reaction. Then we take a look at the acidic, which is going to be this guy. So again, the sodium here is neutral. So really the acidic portion is this guy. Okay, so if this is an acid, we're going to write it paired with water. Water will be the base. With the reversible here, acid is a proton donor, all you'll have left is this guy. This is our conjugate base. Okay, and then over here, because it loses the proton goes onto this guy, you'll have H3O plus AQ. So basically, this is the conjugate base. This is the conjugate acid. So HSO4 is acidic because it releases hydrogen ion. Okay, now the next part on part B is taking a look at these colors here and deciding what pH range of these guys would be. So I'm going to work out one with you guys, hydrochloric acid. Basically, you have to take a look at these colors here, okay? And then there's a chart in your introduction area where they tell you like the color ranges here, okay? So I'm going to take a look at the color and show you the ranges and see how it works. Now there's these two, but sometimes the colors don't print out really well. So I like to just look at this. That one can be just a good guide, okay? So take a look at this. It says hydrochloric acid, when you use bromcresol green, is yellow. So yellow for bromcresol green is basically anything that's 3 pH 3 and under will be yellow. So we just know from this first observation here, we know that HCl has to be less than pH 3. We don't know anything else, okay? Now Congo red here is interesting because it's kind of hard to see the color. There's blue and then there's orange red. So the way I see it, I see here there's like, this is more blue, that's more purple, and that's more brownish. So I would say it would more be in a blue region. Okay, so it's kind of hard to see, but if you stare at it, this is bluer now, and now it's more purple, more to the reddish side, and this is the brown side, okay? So I would say Congo red is on the blue side, it's also less than 3. So basically these two indicators have just confirmed to me that HCl is less than 3. I need to narrow it down to one number though, 0 to 1, 1 to 2, 2 to 3, or 3 to 4. But I don't know which one. So far I know it's less than 3, okay? Now, the next one, we'll look at methyl yellow. So if you take a look, it looks pinkish, reddish, right? So if it's reddish, pinkish, then it looks more red. So the color is between red and yellow. If you look, the other guys have orange and yellow. So this must be the red. So again, it's comparatively, okay? So this is red. So red is good news. So early from these two, I knew it was less than 3. But because it's red, I know it's going to be less than 2. So I just eliminated 3 out of my answer. It's going to be under 2, okay? Now let's take a look at thymol blue's color. So thymol blue's color, right here. Basically, thymol blue is red and yellow range. So I would say this is more the yellow range, and then this is more in the middle, orangey. So this would be considered the red side, okay? So if it's the red side, this I would say it's maybe around 1-ish here, or 1 to 0 over here. So thymol blue here is kind of like purplish. So I would say it's region around red here, okay? So we just said it was less than 3, around less than 2, and it could be around less than 1 or around 1, okay? Now then we take a look at methyl violet, I'm sorry. Methyl violet here tells, so it's not really conclusive. It says it's 1 or less, 2 or less, 3 or less, okay? So let's take a look at methyl violet here. The range here is yellow to purple. So these two are purple here. And I would say it's definitely not yellow, so it's definitely not 0. I would say that possibly because it's this color, it probably is somewhere in between here. I would say it falls probably maybe around 1, okay? So I've kind of figured out that it's less than 3, it's less than 2, it could be around 1, and I just marked down it possibly could be between 1 right here, or maybe 1 and 2, okay? So this is how I'm going to decide that HCl is going to be maybe pH range of 1 and 2. So what you do here is based on these color ranges here, you will put in your answer. pH range of this guy is going to be 1 to 2. Remember, your answer choices are 1 to 2, 0 to 1, 2 to 3, 3 to 4, 4 to 5, 5 to 6, and 6 to 7. Like, these are your only options. You can't go 2 numbers, you can't go whatever, so I'm just going to pick 1 to 2 here. Okay, so that's how we're going to figure out our answers for this part. Now let's take a look at the data for part C here. So for part C, what's interesting is they ask you, oh, so now you have to pour an acid and a base together and you figure out what the pH is. When you put an acid and the conjugate base together, you're making a buffer, okay? So the buffer here, it says here, pH of this and this, it's a buffer system, and it says 4.52, so that goes over here. And then the diluted buffer is basically they add water to it, and then they put that number there. So what's the difference between diluted and non-diluted? Well, it's just got more water, but the ratio of acid and base is still the same, which is really important here. If it's 1-to-1 mole ratio of acid and base, it is actually the best combination of buffer that you can have. So I'm going to go ahead and put this down here. So 4.5 to 4.45. So it says here, take this buffer, and they actually dump the buffer, they split it into 2 parts, and they put a few drops of sodium hydroxide. So it says, going back to sodium hydroxide earlier when I was talking about this, when you put sodium hydroxide in, this happens. It reacts with the weak acid of the buffer to make some conjugate acid and water. So basically, we noticed that the sodium hydroxide pH goes up to 4.45. 4.52. So it's not drastic increase by, let's say, 0.1-ish. Okay, so in the lab question, so ask increase by 0.1 or increase by 7. This is definitely closer to 0.1, okay? Because what was the chemical reaction happening? Because hydroxide was reacting with the weak acid to make some conjugate base. Okay, so you just have to know who's reacting with who, and therefore all you're changing is just the ratio of A minus to HA, which changes the pH a little bit because the formula to determine pH is pH equals to pKa plus log A over HA. So basically the A goes up here, HA goes there, so it changes a little bit, so your pH changes a little bit. pKa is just an intrinsic quality, a number that's based on depending on whatever acid or base you're trying. Okay, so and it says, was the pH drastic after adding HCl, and what was the reaction? Well, when you added HCl, it went down to 4.38. And so basically it decreased by 0.1. Because why? Because we just said earlier that H, incoming strong acid, will react with conjugate base to make some weak acid. So because H plus plus conjugate, so this guy self-sacrifice to make some weak acid. Okay, so let's go to the next page here. The next page says, here's a different buffer now. So this buffer kind of is not a good buffer because it's not 1-to-1, it's like 1 to 10. Okay, so when you have a 1 to 10, what happens here is going to be basically the pH of the buffer. Let's see, this is 5.66. Okay, so they also actually asked for pH of the buffers. Yeah, so let me go ahead and go back over here and show you how to calculate. So if you have pKa, oh, I forgot to tell you guys, if this was pKa, not pH. So anyway, this is pH, I wrote it wrong. So pKa, if the pH is 4.52, the pKa would be the same, okay? Because 4.52, which is the pH right here, equals to pKa plus log of acid, base over acid. And we put the same amounts in here. So this is log of 1 because it's like 15 mils over 15 mils. So let me write it down. That one is 15 over 15 equals 1. Log of 1 is 0. So 4.52 is the pKa right here. Okay. Now for the diluted buffer, if the pH is 4.45, the ratio is still 1-to-1. Therefore, the pH still equals to pKa because the ratio is 1-to-1 here. So that's 4.45. You said it's pH, but it's pH and pKa is the same if your ratio of base to acid is the same. Okay, so this is 4.45 here. Now, when we go up to this side here, this was the pH. Okay, if you have the pH here, now we want to put it in. So the equation here is 5.66, which is pH equals to pKa plus log of, so this time we have 20 of my buffer base over 2, right? So log of 10 is 1, agree? This 20 over 2 is 10. So 5.66 equals to pKa plus 1. So pKa must be 4.66. So that goes over here. Okay? So basically it's just the ratio, the pKa and pH depends on the ratio of your base to your acid. So the next question it says, was the pH change drastic after adding NaOH to the buffer? And what was the chemical reaction? So let's take a look here. Actually, this one cut off. Let me show you the real answer. My printout cut off. I have it on here. It says it was, I believe, like it increased really high, like drastically. It was 11.63 and 5.05. Okay, so question that we want to go back to is right here. It says, was the pH change drastic? Yes. pH increased a lot, so we'll say by 7, because the question is multiple choice 7 or 0.1 after you added NaOH. Because why did that happen? Because so when you add OH in there, you are reacting again, remember, with the base is reacting with the acidic component, which is this guy, to make water and A-. But you only have 2 mils of this, and they poured in they poured in, I think, 3 mils of this guy. So you definitely have too much hydroxide, right? Because all of the HA has reacted with OH, and the buffer basically broke. So the remaining OH increased pH. Okay? Was the pH change drastic after adding HCl to DI water? So adding HCl to DI water, yes, it was drastic. Yes, pH dropped a lot from 7 to 2. So I'll say pH dropped by around 7 because water is not a buffer. And then was the pH change drastic after adding NaOH? Yeah, it went up to 11. So yes, pH increased by a lot, maybe 7, because water is not a buffer. Now, all these questions here will be online in multiple choice form, so you'll have to make sure you select correct answers, okay? Now, so after this part here, they actually ask you to calculate. So this part here, part D, is separate. So let me show you the results quiz real quick before we come to part D. I want to walk you guys through, let me do the screen share real quick. So we're gonna go over to this one. So here's the pH and the colors. You should be able to pick these answers out. They give you their own numbers, but you can actually calculate. Like they'll say, if you make 15 mils of this with 15 mils of that, and then dilute it, the pH is this, what's the pKa? So it's the same thing, like what I just showed you. Basically, in this case here, the pH is equal to the pKa because it's 15 and 15, 1-to-1 mole ratio. And then they ask you, oh, does it increase, decrease? Remember, because who reacts with what? And then you keep going. What happens, what's the reaction when you have 5 drops of strong base added to the buffer? So 5 drops of strong base added to the buffer is going to be basically the one with OH plus your weak acid. So I would say it's going to be this weak acid plus your OH, and you're going to make some conjugate base right here and water. So this is when you put strong base into your buffer. And then they ask you the question here. You're going to do 2 to 20 ratio of the pH comes to here. What is the pKa? This is the one that's a little bit different. We just did where the difference is 1 away. Okay. And then they ask you questions here. What happens to the water? What happens to the pH? Now, this question number 17 here, it says a student needs to prepare a buffer solution with pH 5.36. So this is your pH and equals to pKa of 4.73. And then how many mils of the base? So this is the base part will be needed to add it to 15 of 0.1 to prepare this buffer. So literally you will use this equation. pH, put the pH of 5.36 right here, equals to 4.73 plus log of the volume of B minus, which you don't have, you're looking for, but you have the volume of HB, which is 15. And then you just solve for the B minus volume here, and you put your answer right here, okay? So please make sure you use the correct calculation, correct formula. This one is just follow this formula here. Now part D here is separate. So I'm gonna have to show you some calculations over here. Part D calculation is very different from question 17, which is still in part C, okay? So let's take a look at part D here. So part D, it says here pH of buffer. So you'll have to say pH of buffer that's required is pH 7.0. My pKa that was given was 7.2. Okay, so this is given to you, and then you can calculate how much sodium hydroxide you need. So this is the interesting part. They want you to make a buffer, but they didn't give you any weak base. They gave you a weak acid because I knew this pKa here. So they gave us some weak acid. And that's it. They're like, okay, take this weak acid and take sodium hydroxide and make a buffer. And that's kind of hard because we just learned earlier that buffer, you use either a weak acid and a conjugate base or a weak base and a conjugate acid. How in the world are you going to use weak acid plus sodium hydroxide to make a base? So there's actually a little trick to this guy here. So take a look at this equation down here. So if you had some weak acid and you poured some sodium hydroxide in, you technically can create some of the conjugate base on your own. You create this guy by sacrificing some of your HA. Okay? So let me rewrite this over here. There's the same equation here. So basically, you have hydroxide from sodium hydroxide, and you have your weak acid. We don't know what the identity is, and it's going to help you make some conjugate base plus water. Now, so basically, you know this is what you need to make, but now you're like, okay, so that's an equation I'll have to do. So if I had this guy here, what I need to do is pH is 7 equals to pKa is 7.2 plus log of base, which is A minus over HA, right? And you're like, well, I can do this part, but I don't have this. I have some HA, but I don't have A minus. So I need to create some A minus here. So how do you create A minus? Is by using some sacrificing some of HA. So you actually start with 20 mils of this guy, okay? So 20 mils of your acid right here. And then if you add 1 mil of your base, okay, that 1 mil is all gone. It was eaten up by HA. All you have left is 19 mils of HA. And if you have 19 mils of HA, you actually technically create 1 mil of this. You guys see that? So if I put another extra mil, 2 mils of hydroxide, put that in, now my HA has become 18 mils, and this becomes 2 mils. So basically, if you put in some hydroxide, you use up some of your HA and you make the same amount of A minus, okay? So if I put in Y milliliters of hydroxide, and I start with 20, HA will be 20 minus Y milliliters. Okay? And then A minus would be Y milliliters appearing, because basically this one disappears, it makes this, and this one goes down by that amount. So now I have my ratios right here. Okay? If I solve for Y, I can get the volume of NaOH that I need. So that goes in here. So part D's math is a little unique. It's 7.0 equals to 7.2 plus log of A minus is Y over 20 minus Y. Then all you do is you solve for Y. Okay, you use algebra and you solve for Y, right, whatever the volume here. And the volume I know is used in titration is to take final minus initial, so it will be 8.55 mils minus 0.71 mils. And whatever the answer is goes here. Then you compare what this volume is compared to that volume, see if it's close, does it agree, yes or no. Okay, so that would be what you need to do for part D's question. So let me show you what part D looks like. The question, all you have to do is type it out. So it says, what was the pH of the buffer? It was 7. What was the pKa of the acid? It was 7.2. Show how you calculate how much OH minus, which is the value for Y. And then what volume of hydroxide was added using the titration? How does it compare? So basically that's just what we talked about. Okay, so this is for the results portion. Remember, the most important part is most people forget to use, they get so used to this fancy equation down for question 18. Question 17 is, again, a very simple equation. All you do is put pH here, pKa here, volume of B minus, HB is 15 down here, and you solve for the volume up here. Okay? All right, I hope this helps. Let's see.